Hello class, welcome to SciChem. Here we are another session for lecture 8 of chemical kinetics. So in previous class we have discussed about RNS equation. RNS equation generally the variation of temperature with a rate constant, and we found that the equation K is equal to A into e to the power minus EA by RT, where K is the rate constant for the reaction, A is the collision factor or collision frequency, E exponential, EA is the activation energy, R is the gas constant, and T is the temperature. So basing upon this equation, we have a problem by using RNS equation. Calculate maximum possible value of rate constant. By using RNS equation, calculate the maximum possible value of rate constant, or calculate value of rate constant, or calculate value of rate constant at sufficient high temperature. This equation is also called this question I can also write calculate value of calculate value of rate constant at sufficient high temperature, or by using RNS equation calculate maximum value of rate constant. We are solving the answer. Calculate the value of rate constant at sufficient high temperature means I can take sufficient high temperature T tends to infinite. We have the equation K is equal to A into e to the power minus RT. So limit T tends to infinite, A is equal to limit T tends to infinite A into e to the power A by RT. Again, limit T tends to infinite is equal to limit T tends to by 0. In case of T tends to infinite, I can write, T tends to infinite means I can write 1 by T tends to 0. I can write in case of T tends to infinite, I can write 1 by T tends to 0. So here A into e to the power minus EA by RT. So here 1 by T is 0. If 1 by T is 0, 1 by T is 0, e to the power minus EA by R is also 0, e to the power 0 will be 1. So limit T tends to infinite, K is equal to, so the maximum value of rate constant will be A at a high, very high temperature. Then come to next part. We have K is equal to A into taking A into, so A is equal, since this equation is ln A into B, I can solve this ln A plus ln B. So ln A plus 0 power that will be ln K is equal to A ln into E cancel with each other, so we get A by equation A is equal to 1. Again, by converting to log, I can write the above equation as log K equal to A minus ln 2. Solving this, I can get log K is equal to log A minus EA by 2.303 RT. So the variation of rate constant with the temperature have a graph. If we plot a graph between the ln K and 1 by T, so I can put y is equal to C plus minus of m, y is equal to C, y is equal to mx plus C. So what is x? The x is 1 by T and slope will be negative, that is EA by R. Y is ln K. So this is the by solving this is the equation of straight line. Each intercept having maximum value A and slope is negative. Okay. Similarly, if the graph is asking between log K T, so same, y is equal to T minus x. So that is also equation of straight line. Intercept log A, the slope is negative by. So these are all regarding RNS equation. Now come to another part, variation of rate constant with two different temperature. If two different temperature are given, what will be the rate constant? So while doing such thing, variation of rate constant with two different temperature, you have to consider EA, that is activation energy, enthalpy and frequency factor are assumed to be independent of temperature, less otherwise mentioned. So while doing such thing, you have to consider activation energy, enthalpy and frequency factor are assumed to be independent of temperature. So again we have K is equal to A into A by RT. Let T is equal to temperature 1. Then rate constant K is equal to K1. So I can write here K1 is equal to A into e to the power minus EA by RT1. Similarly, let T is equal to T2, K is equal to K2. K2 is equal to here K2 is equal to A into e to the power is by dividing K2 by K1 to A into e solving this equation K1 here e to the power minus a by rt2 divided by e to the power minus a by rt2. If I take e to the power rt1 to above, right here K2 by K1 is plus a by rt2 plus so I have K2 by K1 equal to 0 power, if I in common a by r, a by r right here by K1 on taking ln on both sides, ln K2 by K1 ln into r by K2. So ln cancels with each other, right here ln 2 by K1 r. This is the variation of rate constant with two different temperatures. If I have to convert ln into log, I can write here log K2 by K1 is equal to A by K0. Okay. This is so this is variation of rate constant with two different temperature. Variation of rate constant with temperature means RNS equation, but here we have two different temperature with two different rate constant. So we are coming to next part, that is, so we have already completed effect of temperature. Effect of temperature involves RNS equation, collision theory, etc. Next come to another part, effect of catalyst. So what is catalyst? So there is a scientist Berzelius. He observed that heating of potassium perchlorate results Cl plus, but when added slight manganese dioxide, he also observed it gives product KCl plus O2, but the formation of O2 is reached. That means rate of reaction is increased by adding manganese dioxide. So manganese dioxide acts as a catalyst. So what is the effect of catalyst on rate of reaction? A substance which alters the rate of a chemical reactions is known as catalyst, and phenomena of changing rate of reaction by the use of catalyst. So a substance which alter the rate of a chemical reactions are called catalyst. So there are various points regarding catalyst. The first point is positive catalyst increases rate while negative catalyst decreases rate. So what is the effect of positive and negative catalyst? If I have to consider, let us consider a graph. And we have graph between potential energy coordinate. So we have already studied this type of graph. This is reactant of reactant of product. The peak is full energy, and it is the amount of energy must be supplied to reactant molecule, that is action. This is it. So positive catalyst increases the rate while negative catalyst decreases the rate. That means catalyst provides yeah, catalyst provides an alternative path reaction in which threshold energy will change, due to which activation energy changes and due to which rate of reaction also changes. That means catalyst, what catalyst do? Catalyst provides an alternative path. If this is the path of reaction, that is reactant to product, if this is the path of reaction, what is catalyst do? Catalyst provides an alternative path. That means this is the path. In this, the threshold energy decreases, so this much amount of energy is required to proceed the reaction. If threshold energy changes, then activation energy also changes, and this is use of positive catalyst. If we are using negative catalyst, then what happens? The threshold energy increases. If the threshold energy increases, that means we have to supply this much amount of activation. So this graph shows use of negative catalyst. So positive catalyst decreases the rate of reaction, positive catalyst increases the rate of reaction by lowering threshold energy, and thus by lowering threshold energy, activation energy also decreases and rate of reaction increases. But by using negative catalyst, what we have observed, it chooses a alternative path that will increase the threshold energy. Due to increase in threshold energy, activation energy also increases, and due to increase in activation energy, there is a net decrease in rate of reaction. So we have 2 points: positive catalyst increases rate while negative catalyst decreases rate. So what is the role of catalyst? Catalyst provides an alternative path reaction in which threshold energy will change, due to which activation energy changes, and due to which ROR, rate of reaction, also changes. Then come to next point. catalyst never consumes during the course of reaction. That is also true, because catalyst does not participate in a chemical reaction, but it can alter the chemical reaction. Catalyst does not change average energy level of reactant and product. Average energy, here the it is reactant, is product. So what you have observed, this line shows without catalyst, this line shows negative catalyst, this line shows positive catalyst. It is the average energy level of reactant and product, and it does not changes the average energy level of reactant and product. If the catalyst does not change the average energy level of reactant product, so catalyst does not change thermodynamic, here thermodynamic behavior of any chemical reaction, that is delta H. So delta H for that reaction remains same whether you are using negative catalyst or positive catalyst. So in order to carry out a reaction, catalyst is required in small amount. So these are all the basic features of catalyst. So variation of K on addition of catalyst. So what is the effect of variation K on addition of catalyst? Again we are using RNS equation, that is K is equal to A into e to the power minus A by RT. So without catalyst, I have activation energy EA and rate constant is, so K is equal to A into e to the power RT. Consider is 1. With positive catalyst, I have another activation energy, consider EA dash and rate constant, such that for EA dash I can write here, by using positive catalyst activation energy decreases, here by using positive catalyst activation energy decreases, so I can write here such that EA dash is less than E. By using positive catalyst rate of reaction increases, then rate constant also increases, here K dash is greater than. So the new rate constant equation will be K dash is equal to A into e to the power minus A by T. So dividing equation 2 by 1, have K dash by K is equal to A into e to the power minus A dash by RT divided by A into e to the power. So AA cancel with each other, I can write here e to the power 1 by RT to A minus e to the power minus A by RT is taken above, so it will be plus A by RT. If I take common 1 by RT, then it will be A minus A dash. So again K dash by K is equal to e to the power 1 by RT plus dash, multiplying on both sides, right? On on with it have S by EA minus EA dash by RT. If I have to convert ln to log, the request be log K dash by K is equal to EA minus E dash by 2. So this is all about variation of K on addition of catalyst. Then come to another part, more and more important. We have not discussed about molecularity of the reaction. We have discussed about order, what is order, but we have to discuss about what is molecularity of a reaction. So let us consider mechanism of reactions. So on the basis of mechanism of reactions are classified as simple reaction and complex reaction. So what are simple reactions? Simple reactions are also called elementary reactions. So come to the part simple or elementary reaction. What are simple or elementary reaction? Reactions which get completed in one step are called simple or elementary reaction. So reactions which are completed in a single step are called simple reaction. And in this simple reaction, these reactions does not involves any reaction intermediates like your carbocation, C plus, carboanion, and free radicals. These are reaction intermediate, but reaction intermediates are not involved in elementary reaction. If we consider for an elementary reaction, we can define molecularity of the reaction. For elementary reaction, we can define molecularity of the reaction, and it is equal to number of molecules which makes transition state or activated complex because of collision in proper orientation with sufficient energy. Or we can simply define molecularity of a reaction may be defined as number of molecules which collide simultaneously in order to form a product. While collision, they should have proper orientation with sufficient energy. The reactant molecules should possess proper orientation and sufficient energy. So as the elementary reactions are completed within a single step, for elementary reaction we can define molecularity, and molecularity of the reaction is equal to number of molecules which makes a transition state or activated complex because of collision in proper orientation with a sufficient. And on the basis of, if I draw a graph, A gives rise to product, then if I start A, then it will give product, and this is the transition state. Since the reaction is completed within a single step, A gives rise to transition state, then P, and a transition state is not an intermediate. Remember, transition state is not an intermediate. So since this reaction is a single step reaction, for single step or elementary reaction I can define molecularity, and on the basis of reactions are classified as, if A gives rise to P, that means M equal to 1, that is molecularity is equal to 1, that is called unimolecular reaction. Molecularity, on the basis of molecularity reactions are classified as unimolecular. If A plus B gives rise to P, that means A plus B is the simple reaction and two reactants are present, so molecularity I can write M is equal to 2, that is bimolecular. If A plus B plus C, that will give product M is equal to 3, tri or termolecular reaction. and molecularity is always positive integer, that is it cannot be negative 0 or fraction. Molecularity is always a positive integer, it cannot be negative 0 or fraction like order. And it has been found that reaction having molecularity greater than 3 are very rare. Molecularity either 1, 2 or 3, but molecularity greater than 3 is very rare. Why? Let us consider a beaker, another beaker. Here, two molecules are present. Here, three molecules are present. Here, four molecules are present. 1, 2. So, in which beaker probability of simultaneous collision, probability of simultaneous collision. Here two molecules will collide at same instant. Here three molecules will collide at same instant. Here four molecules will collide same instant. What is the probability of collision? On moving from 1 to 3, the probability of simultaneous collision decreases. The probability of simultaneous collision decreases. Since the probability of simultaneous collision decreases, so molecularity greater than 3 is very rare. Since a simple reactions are completed, let's come to another part. Since simple reactions are completed in single step, so that will be the rate determining step. So RDS means rate determining step. So order of the reaction will be equal to its molecularity. Let us consider reaction H2 plus I2 gives rise to 2HH. Since this is the simple reaction, I can write molecularity. Two molecules are present, then that will be equal to order 2. So this is rate law equation. Rate is equal to K into H to the power 1 into I to the power 1. If I have to consider another example, 2A plus B gives rise to product. If this is simple reaction, then I can write here molecularity is equal to order equal to 3 and rate is equal to A to power 2 multiplied by B to power 1. But if you consider another equation, N2 plus 3H2 gives rise to 2NH3. Here molecularity is equal to 4. But we have seen that molecularity should not be greater than 3. And molecularity greater than 3 are very rare. So molecularity is equal to 4. Molecularity is equal to 4. That means it is definitely a complex reaction. So we are coming to next part, that is complex reaction. So what are complex reactions? Reactions which are completed in more than one step is known as complex reaction. Let us consider a reaction A gives rise to B. If we observe the reaction mechanism right here, first A gives rise to C is step 1, then C gives rise to D, that is step 2, then D gives rise to A step. So A react gives rise to C and C reacts gives rise to D and D gives rise to B. So here C and D are reaction and here in case of a simple reaction, no reaction intermediates are formed, that is simple reaction A gives rise to P. But here if we consider a reaction A gives rise to B, the reactions are completed in more than one step. So if A gives rise to B, we have observed that these are three steps of reaction. So reactions which are completed in more than one step is known as a complex reaction. And complex reaction involves reaction intermediate, and its detailed step-by-step description of any chemical reaction is known as mechanism of the reaction. So complex reaction involves reaction intermediate, and its detailed step-by-step description of this reaction is known as reaction intermediate, known as mechanism of the reaction. If we are observing this graph here, this is the reactant, this is the product, and this is the transition state is being formed, and this is intermediate is being formed. So what happens if we consider our reaction A gives rise to B, and for this reaction I can draw the graph as follows. This is potential energy, this is reaction. Consider I have reactant A and B. So what is this is transition state 1, and this is C, that means this is what is C? C is reaction intermediate 1, this is transition state 2, this is C, that is reaction intermediate 2, this is transition state. So from this to this is first reaction A to C, from C to D another reaction, D to B another reaction, where three transition states are formed, and by observing reaction A to B we have two reaction intermediate, that is C and D. So this is one step of the complex reaction, this is another step of complex reaction, and this is another step of the complex reaction. So here next important point, different step of complex reaction have different rate, and slow step is the rate determining step. Different step of complex reactions are different rate, and slow step is the rate determining step. If we consider slow step means activation energy should be high. If we consider this step, the activation energy is high for A to C. For A to C, the activation energy is very high. As A to C, the activation energy is very high, we can observe that this is a slow reaction. So different step of complex reaction, different rate, and slow step is the rate determining step. So A to C is our rate determining step. A to C is our rate determining step. And reaction intermediates are, come to next part. Reaction intermediates are highly unstable. They form after reaction is started and destroyed before the reaction gets completed. So what happens here? Reaction intermediates, the C and D are highly unstable. Here the C and D are highly unstable. They formed after the reaction gets started. When reaction starts, they will form, and before the reaction is completed, they will get destroyed. So reaction intermediate cannot appear in rate law equation. This is important. So this is all about mechanism of the reactions. And the slow step is the rate determining step. Another important point is there, I can write here. For complex reaction, each step should be considered edge elementary reaction. For complex reaction, each step should be considered as elementary reaction. This is step 1, step 2, step 3. Each step is considered as elementary reaction. For each step, order equal to, and order we can calculate for flow reaction, that is the rate determining step comes in rate law reaction. But molecularity for overall reaction is meaning molecularity of our overall reaction is meaning less. So this is all about molecularity and mechanism of the reaction. For mechanism, we have two types reaction, that is simple reaction and elementary reaction. Just observe the graphs related to simple reaction and complex reaction. For complex reaction, molecularity is meaningless, but for elementary reaction, molecularity is equal to order. And remember, for complex reaction, slow step is the rate determining step. So this is all about reaction mechanisms. Thank you.